So remember, what's on the quiz on Thursday? Something like this. You might get 2 of them. It's so important. It says for each situation, I want you to draw a free body diagram, write down Newton's laws, Newton's second law equations. And then we want to talk about what really caused the acceleration in this case here. So here we go. So here I'm going right to the free body diagrams and not the indication one. Okay, so I'm going to start off with A. So when I look at A here, what you're seeing here is that I'm really going to focus on this guy right here. Where am I at? So I'm looking just at this guy right here. And what you're seeing here is that there are 2 objects, right? If there are 2 objects, then that means I have to write 2 sets of forces here. So let's go look at this thing. So the fact is that there are 2 objects. Okay, if there are 2 objects, that implies that there are 2 free body diagrams, and therefore there should be 4 sets of N2L, two sets of N2L equations, 1 for each object. So let's go look at this now. So the first thing I'm going to do here is that I'm going to look at object 1 or mass 1. So if I look at mass 1, what do I see? What I do here is that I come over here and I'm literally going to do what? I'm going to focus on block 1. So that means I'm going to come in here and I'm going to do what? I'm going to isolate 1. Right? I'm isolating 1. I reduce it to its center of mass point. So now when I'm looking at this thing, that's object 1. So when I look at this thing, I see that there's a normal force and I see that there has to be the force of gravity. So in this case, we're saying that since the block is more likely to remain on the surface, we then say that we have balanced forces vertically. So I have the force of gravity. I have the normal force, and look how I'm drawing them. There should be the exact same length. So if it's 3 up, it's got to be 3 down. Now, should I assume friction in this case? It doesn't say that there's no friction. Oh, it does right there. It says no friction. So if there's no friction, what are the forces acting on block 1 horizontally? Well, we know that these guys, the assumption is that it is accelerating. So look, there's a force F here. So if I look at this force F, what I'm going to do here is that you could come in here and I could do what? Well, I know that if it's accelerating, I have to have unbalanced forces. So let's say that in this case, this has to be the force F. This is the one that's acting on block 1. So I'm going to call this just the force F because that's what it's doing there. Does block 2 interact with block 1? According to Newton's third law, absolutely. So if there's a force, then that means here there has to be a force that's doing what? That has to be shorter than this force. So this is the force of 2 acting on 1. And this guy is from Newton's third law. There has to be an equal and opposite force. So when you look at this, look at the length of the net force now. The net force has to be what? So if I look at the net force, how long should the net force here? So if I count the purple, it's 1, 2, 3, 4 squares. If I count the red, it's going to be 1, 2, 3. So therefore, the length of this guy should be 1 square. That's the net force acting on mass 1. So now I come in, I've written all my forces. Here's my direction of velocity, so that's plus, minus, plus, minus. Then I start writing Newton's second law. So I have this force, and here I go.
Hey, Carlos.
Yes.
Would you not include the force of 1 acting on 2?
No. Because the only force that you can see is the force of 1 is that force F. But the interaction between 2 and 1 is not in the forward direction, it's in the backwards direction. Now, if I was looking at block 2, then that would be the force of 1 acting on 2. Does that make sense, Tessa?
I guess I'm just confused on why it would only be going in one direction and not in both.
Here, how about if we do the second mass and see if it makes more sense?
Okay.
So just hold. So then if I look at this thing, look at the signs. The number one error in Newton's second law in writing the equations is the sign. Look at F. F, purple, is pointed to the right, plus. I look at F12, it's pointed to the left, so it's minus F21. Is this thing accelerating? Yes. What is accelerating? Mass 1. That's what's accelerating. So what's the cause here? As we already said here, what caused this thing to move forward? Right? What caused this thing to accelerate? It's not the force F. This is the cause of the acceleration. It's F minus F21, not the force F. It's very common for people to say it's the force F that's the cause. That's not the case. Okay? So the question is, shouldn't the horizontal forces be equal according to Newton's third law? No, not at all. Only the interacting forces, the force between 1 and 2 should be the same, not the purple force. The purple force is outside block 1. And I'll explain that in a minute here. So then look at the forces in the y direction. Look at the normal. Normal's in which direction? The positive. Look at the force of gravity. It's down. Is it accelerating in this vertically? And we already said no, because it's in static equilibrium. Once again, F did not make this block accelerate. It's F minus F21. Let's go to the next one. So now let's go focus on mass 2. So if I do this, what I really want to focus on is that I want to go in and I want to do this guy again. And then I want to ask the question, let's isolate block 2. So when I isolate block 2, what is making block 2 go forward? You got to say it's block 1. So here I go, center of mass. That's my mass 2 right there. So according to Newton's third law, the force of 2 acting on 1 is the same as force of 1 acting on block 2. So if that is 3 squares, then this has that force right there. And then this force is 1 on 2. You know, here's another question that you could ask yourself, Tessa. When I'm looking at block 1, what would happen if block 2 was not there? Isn't block 2 making it harder for block 1 to go forward, to accelerate forward? The answer is yes. And you might say, oh, it's because of the mass. It is not because of the mass. It's because of the force that 2 applies on 1 in the backwards direction. And the same thing happens here. When you look at the force of 2 on 1, that's what's making this thing go forward. So then I'm assuming that mass 1 is larger than mass 2. So then my normal forces should be what? Should be smaller for 2. And then my force of gravity should be smaller for 2. So then, now that I see that, they're both accelerating at the same rate. So therefore, when I set up my coordinate system, I'm going to use the same sign convention that I did before here. And so then we could come in and we could do that. So now, if I look at this thing here, you could then say, I come in and I look at these scenarios here, and you could see that I have what? F12 is in the positive direction. What mass am I accelerating? Mass 2, not mass 1. So what caused this thing to accelerate? And clearly, the cause of the acceleration is the force of between 1 and 2. And then, just as we did before, I have N2 minus Fg2, and because it's in static equilibrium, I put 0 here. So what you're seeing here is that I have my Newton's equations right here. Right? I have my Newton's equations right here. What am I looking for the quiz? Exactly this right here. So what I want to go do is I want to go look at the next one. So here we go.
Real quick, for mass 2, why isn't block 2 exerting a force on mass 1?
It does in mass 1, F2.
Oh, right. Okay.
Okay, let me go get the next image. Okay, here we go. Okay, so here's B. So remember what I said about coordinate systems. Okay, the first thing that you should do when picking a coordinate system is look at the direction of motion. When you're looking at the direction of motion, make sure that motion is along one of the coordinate axes. It will really save you an enormous amount of energy. There's only one situation in this course, which I don't even think we're going to get. It's essentially when you have a car going around a bank. That's the only time that it may be more useful not to do that. But here we go. So what am I going to do? I'm going to isolate the box. What do I mean I'm going to isolate the box? I'm going to draw my incline. And I'm going to replace the box with a dot. And then I'm going to come in here and I'm going to just say, what are the forces acting on this block? So the obvious one is that we have the force of gravity. Okay. Another one that seems to be a good one here would be what? The normal force. Look perpendicular. It's got to be perpendicular to the surface. And then you have this force F here. Okay, so in this case, you're seeing this force go like this. And I agree, there's an angle on this incline, which I really don't care about. Now that we got all of the forces, there's no other forces acting on the system. Remember, we want to draw a coordinate system now. Number one rule, always pick direction of motion to be along one of the axes. So since the block is moving in this direction, I'm going to pick this to be what? My positive x-axis. And since this is perpendicular, this automatically becomes my positive y-axis. And so when you're looking at this thing, the only thing you could see here is that I got to draw vector components now. And so when you look at this thing, note only one vector lies along that axis. And under rule number 2, you would say, no, I should line up the other way. But rule number 1 is pick the axes as one of the directions of motion. That overrides that rule. So what you're seeing here is that now we need to break the vector components, the vectors, into components. Now, we don't really care about the sines and cosines right now. I am not interested in that. I am interested in just getting the general shape. So check this out. I got to project the y and the x component. So all of a sudden, I really have an x component that's where? In that direction. I really have a component that goes where? In the y direction. Okay, and then I do the exact same thing with the green vector. I have a y component and I have an x component. So then I see that the force of gravity has an x and the force of gravity has a y component in this coordinate system. So that looks messy, but what should it really look like? A free body diagram only has components, not vectors. In other words, what I really would like to see is this, that when I look at this thing and I have my coordinate system like this, there's really what? There's a normal force in this direction. There's a force in the x direction. There's a force in the y direction. There's a force of gravity in the y direction, and there's a force of gravity in the x direction. And so once I have this, I know this is positive, positive, negative, negative, and I know that I'm speeding up now. So what that really means here is that I need to be a little bit more careful. I have an unbalanced red force here. So in other words, this force in the x direction must be larger than the force of gravity in the x direction. So here we go. Now I write Newton's second law. Okay, if I write Newton's second law, then I start to look at my picture. What is in the positive x-axis? F of x. What's along the x-axis that's in the negative direction? It's minus fgx. What's the common thing to say? What pushed the block up the incline? They're going to say, oh, it's the force. Bullshit. It is not the force. What's the cause? It's the f of x minus the force of gravity in the x direction. That's what the block feels. It doesn't feel the force in the x direction. It feels the difference of these two right here. So what's this? This is the cause of the acceleration. And when I look at the normal in the vertical direction, then I could see that the normal's in the positive, and look at these two forces in the y direction. They're both in the negative. So that means Fy minus Fgy, that this is what's causing this to be balanced vertically. Okay, you could see how this language gets slippery. The force F does not accelerate the block up the incline. Even though people say that, that's incorrect. It's f of x minus f of g of x. This is the net force. That's what causes the acceleration. Okay, let's, I have one more example, and then let's move forward. Okay. So the last example looks something like this. Let's see, where are we at? And this is our last example right here. Again, how many blocks? 2, that means 2 free body diagrams and 2 sets of N2L equations. So here we go. So I'm going to focus on what? Mass 1. So when I look at mass 1, we clearly have a block. And since we're not including friction here, you could see that this is the block right here. And this is block 1. And what I see here is that there's this tension force that's actually pulling on this guy. So then what am I doing? I'm going to isolate it. And as I isolate it, that means I replace this with what? Its center of mass. Well, the fact that this is being accelerated to the right, because that's what the premise is in these things here, then I could see that, well, it's in static equilibrium vertically. So that means here that the normal on block 1 here must equal the force of gravity of the block 1 here. So the only thing that's accelerating this thing to the right has to be what? Has to be the tension. So then once I have established this, this seems like a fairly straightforward equation, right? There's only one force going to the right, so here I go. I got to start summing all the forces acting on block 1. So clearly this only has what? Tension is what? In the positive direction. And since there's nothing opposing this, what block am I accelerating? M1 times the acceleration. Again, here's our cause. In other words, that's the net force. That's what's making this thing accelerate. When I look vertically, we could see that this is very similar to our previous cases. And because we assume that that's on the surface and does it move, then we have this scenario here. So here we go. We have our free body diagram and we have our N2L equations. Now let's look at the other block here. Now, one of the things that I should be very, very careful here is that the pulley is massless. So what does that mean if I have a pulley like this? So if I have a pulley, and let's say this is my pulley here, and what you're going to see here is that I'm going to draw the same rope on both sides. So that means if I draw my rope, let's say that this is my rope here, and this is my rope there. And what you're going to see here is that there are 2 ropes that are really hanging over the pulley right here. So this is tension 1, this is tension 2. If a pulley is massless, then what we say here, then tension 1 is exactly the same as tension 2 when you have a massless pulley. If the pulley is massive, that is not the case. So that means if I look at this scenario again, then you find here is that tension 1 is not the same as tension 2. And what you find here is that this kind of question is what we deal when we deal with the concept of torques and rotational motion. So this does not come for quite some time. So just note that in all of these problems, you must have massless pulleys in order to make this work. So in other words, when I look at the system, if this is the tension here, then the tension on the other side of the pulley is exactly the same. There's no difference in those two tensions. Now let's go do mass 2. So what I'm going to do here is I'm going to take this with me, this image here, if I can get it, and I want to bring it down here with me. So what I'm doing now is that I'm focusing on the block here. So if I focus on this guy and I say, what are the forces acting on them? Well, here I go. I start with my incline again. And what do I do with a block 2? I make it into its center of mass location. Look at the force of F now. If this thing is accelerating, then we know that the force of F has to be bigger than all of the other forces. So I'm going to draw the force F at the end. So here's what I do know. I know that this is going to be the normal of 2. I know that the force of gravity always acts straight down. And you can see here is that there's a tension force. Now note, I can't really draw the same tension exactly the same, but I'm going to try to draw it roughly about 2 squares. So if I try to do that, you could imagine that this guy's going to look maybe something about that length. And what I'm trying to draw is I'm trying to draw the tension here to be exactly the same length as this tension. Why? Because massless pulleys don't change the tension. So now, before I draw in F, what I'm going to do here is that I'm going to do something that I probably shouldn't do, but check this out. I'm going to set my coordinate system. Why is that the positive direction? Because the velocity is in that direction. So I have my negative sign. So now look at my green force. What do I got to do? I'm going to project it. There's F of gy. Then I'm going to project green. And that guy is FGX. So what you're seeing here is that in order for this to accelerate, what actually has to happen? The force F must be bigger than FGX and the tension. So I'd have to draw this long enough to make sure that F is bigger than that. And if it looks like it's the same, then draw yours longer. But I'm purposely trying to draw F to be longer than the combination of T and FGX. So then, here I go. I start doing this. Okay. So if I look at this thing, then I go, okay, what is in the positive X direction? It's my force F. What's in the negative direction? I look at the tension, and then I look at the force of gravity. That is my net force. So what causes this block to accelerate? F minus T minus FGX. That's what makes this thing accelerate.
Carlos, when writing, this down, does it matter whether you put the minus tension first or the minus gravity first?
It does not matter.
Okay.
It does not matter.
All right.
So what mass am I accelerating? 2. So it's
Yeah.
got to be mass times acceleration of 2. And then when I look at the vertical ones, why is this thing in static equilibrium vertically? Because N2 balances out FGY. And this guy is 0. That's Newton's second law. And I really wanted you guys to conceptualize this because the next chapter is ruthless. Now we start calculating numbers. Now we start looking at components. My whole goal is to get you to visualize this without components. That's what I'm going to quiz you on Thursday. So look, no angles, right? Even though I should have angles in here, I don't have angles, right? You got to really pay attention to that.